What was I defining? Oh, compatible sequence, that's right. So, I gave a definition a couple of days ago, and then we didn't really ever think about it again. But we're going to think about it a bit today, so I'm going to rewrite it. So a compatible sequence, what's the word? There's a begins with S, series? System, that's it's a great word, because it doesn't really mean anything. Like a sequence or they all have meaning. System just, I don't know what's a system. A compatible system just means like a bunch of stuff. A compatible system of lambda Radix-Galois representations. There. It's just such an incomprehensible definition because it's such a huge amount of data that you just can't really imagine where it would ever come from. A compatible system of lambda Radix-Galois representation, so I guess these would be rho lambda from gal k bar over k, gal k bar over k to g l n, and I guess it would go to E0 lambda, maybe bar if you like. A compatible system of lambda Radix-Galois representations there. So here, so what's lambda? So lambda is running through the finite places. I haven't really started yet. I'm just writing down a definition we've had already. Lambda running through the finite places of E0. A compatible system of lambda Radix-Galois representations is all of these, right? So it's infinitely many rows, right? You know, well, maybe I should put that. For all lambda finite place of E0, maybe that's where it should go. For all lambda finite place of E0, a representation rho lambda, da 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 da. I've said that bit now, so I can rub it off. So at the minute, that's a system, but they're not compatible, right? Because now all I've got now is for each, you know, if E0 is the rationals, then I'm saying for each prime number L, I've got an L-adic representation. But why they're compatible is the following miracle. Because I've got some other piece of data as well. It means for all primes P, finite places of S, for P, no, finite places of K, P not in S, these are kind of the unramified thing. The idea is S is the primes where the representations are all poorly behaved. So now let's take a prime where this whole system's got good reduction somehow. For all P finite places of K, P and S, a polynomial. Now that's going to be called Fp of X. And that's just simply going to be in E. All these E lambdas are completely unrelated, right? There's the 2-adic numbers, the 3-adic numbers, the 5-adic numbers. But they all contain E0. Like, you know, the p-adic numbers all contain the rationals. So this polynomial here has got rational coefficients, or in this generality, in E0 of X. There. These are all going to harmonic degree n, right? Because they're going to be Char polys. So we've got all these representations, rho lambda for all these places lambda, and we've got for all finite places we've got an FP, such that for all lambda place of E, and for all P not dividing L, where lambda divides L, and also P not in S, and rho lambda is unramified at P, and rho lambda from P has Char poly Fpx, and the miracle is that this is independent of lambda. So we've got loads and loads of different representations, but they all have the same Char polys. This is still, I'm just writing it up again because it sort of blows my mind that such a thing could even exist. So let me flag 2 examples. Right, one, let's have a Dirichlet character. Chi z mod nz star to c star. So that's completely wrong because they're not p-adic representations or lambda-adic representations. This is one complex representation, but this is a finite group, right? This is not a mysterious thing. This is a finite group. So the image of this is just like contained in some, it's just chi of some random number. It's just a dth root of unity for some d, right? D, whatever, is the Euler phi function of n or something. So this just factors through q, whatever, zeta d, that lives in there, star, right? Where d is, if you like, the Euler phi function of n. That would work fine. Right, every element in z mod nz star has got some finite order, and the order of this group is the Euler phi function, phi of n. So every single thing here has got, you raise it to the dth power, you get 1. So when you hit it with the group homomorphism, you raise that to the dth power, you get 1. So it must be a dth root of unity. So there's my E0, right? E0 is q zeta d. Okay, and that's one representation. And now I'm just going to do the dumbest of things. I'm just going to say, well, that's one representation to GL1 of E0, and E0 lives at all these things. So now we've got our compatible system in a completely stupid way, right? So K can be Q, S can be the primes dividing N, right? There, and now I've got rho lambda, here it goes, so rho lambda, it goes from gal q bar over q, some insanely complicated group, I just surge x by Galois theory, z mod nz star, that's gal q zeta n over q. You see, this is a common theme that you just have to get your head around in this. There's always 2 number fields kicking around. There's the K number fields and there's the E number fields. And I've tried to be really, really careful in this course to call all my local and global fields whose Galois groups we're considering Ks, and all the number fields Es, because I was just confused when I was younger especially when I was learning about Hodge-Tate stuff. Like Hodge-Tate theory says something about p-adic Galois representations, and I was thinking, let's just let K be QP, and then the representations to GLN of QP, and everything would be QP, and I would never really differentiate between them, and actually after a while I found this added to the confusion. And actually I was better off thinking about p-adic Galois representations of gal K bar over K, where I reserved the notation K to mean a p-adic field for which Fontaine's theory works. So I've tried to be really careful with these K's and E's. So K is Q, and rho lambda goes from gal Q bar over Q to gal. The reason I mention it is like there's Q zeta n, and there's Q zeta d, and d is not equal to n, and it looks a bit confusing, but it's not confusing because this is the K side, and this is the E side, so they're allowed to be completely unrelated number fields. There's rho lambda, gal Q over Q, to gal Q zeta n over Q, and that's canonically z mod nz star. And that goes by chi to C star, except I've rigged it so it lands in E0 star, E0 star, and then that goes into E0 completed at lambda star. Like if this was the p-adic, if that's the rational numbers, that's just the p-adic numbers, the l-adic numbers, and that's GL1 of E0 comma lambda. Right? So there is a really stupid example of a compatible system of Galois representations, and it's really stupid because it's all the same representation. There's just one representation here. It starts at gal Q bar over Q and it ends up here with some finite image subgroup, and then all I'm doing is I'm just pretending it's a lambda-adic representation by just embedding that in there, right? So this is easily checked to be a compatible system, because the amazing thing about the compatible system is everything is independent of lambda, right? All this thing is like this amazing matrix here has got some char poly that's independent of lambda. And the reason that's true is because that matrix is living in here. It's a 1-by-1 matrix with coefficients in E0. And then you can pretend it's in E0 lambda for any lambda, but it doesn't change, right? So this is easily checked, or relatively easily, I mean in comparison to the thing I'm about to say, easily checked. This is a compatible system. Right, and in fact, Fp of x, k is the rational numbers here, right? So S is the primes dividing n. So if p doesn't divide n, and p is not equal to L, well, there's not even an L, is there? Fp, if p doesn't divide n, I can just divide Fp of x to be, it's got to be a monic, it's got to be the char poly of, it's just going to be x minus chi of p. There, right? Because remember that p, remember there's a dictionary here. This contains frob p, which is some fancy thing possibly defined by some local Galois groups or something. This is a canonical isomorphism, so you'd like to think that that went to something sensible. And this is a random element of z mod n z star that's all we know is attached to p in some way, and p doesn't divide n, so believe it or not, it's the number p, right? So here's some fancy Frobenius elements at p, but via this kind of canonical dictionary, we just get the number p, and lo and behold, p goes to chi of p, and there it is, right? So here's what I'm saying. Here is one-dimensional representation to GL1 of E0, and there's only one representation. So obviously, the char poly of rho of frob p is independent of any choices because there's only one choice. And now we're going to stupidly make infinitely many representations by just pretending that E0 is a subfield of infinitely many p-adic fields, right? Obviously, you get a compatible family. So there's a compatible system of Galois representations attached to a Dirichlet character, okay? And now let me do, here's example 2. Let's choose an integer n, okay? N equals 1 is a fabulous choice, e.g. n equals 1, right? So we choose a random integer, and I'm going to give you a compatible system of Galois representations attached to that integer. This is warm-up, right? Because we're all still half asleep. So this is me waking you up by easy examples. How else can you possibly understand a vastly complicated definition? Right? What is the way? I'm not talking about as a mathematician. This is a weakness of mine, really. How do I personally understand really complicated mathematical definitions that don't really fit in my head? All I do is I work out examples. That's what I do, right? And that makes me a poor mathematician in some sense, because I know mathematicians that don't need an example. They're just quite happy to work with complicated objects without ever needing to see an explicit example worked out. I am not that good. I need examples. So here's another example, right? Here n is an integer, and all you do is you take the cyclotomic character to the power n. So gal q bar over q. So k is q, because it's already hard enough, right? And E0 is also q in this one. And all you do is we do the cyclotomic character. I call it omega. It's not standard notation. That's what we're sticking with. Omega L, gal q bar over q. And this surjates onto gal q zeta L to the infinity over q, which is just the union, remember, of gal q of these q zeta L to the n's. And this Galois group, if you believe that Galois group there, q zeta N over q, is z mod n z star, then just by taking the limit, whatever that means, this becomes canonically isomorphic to zl star. Right? There's the cyclotomic character, and now all I do is I embed this into GL1 of QL, because it obviously lives as a subgroup. Right? And just the same story. If you believe that rho of frob p matches up with p, it's just the same story here, right? So here S is empty. S is empty, and Fp of x is x minus p again. No, it's not even x minus chi p, it's x minus p, right? And lo and behold, omega L, if p doesn't equal L, omega L of frob p is some element of this group, and via this canonical isomorphism, this gets sent to P, right? So frob P here ends up at P, and there's just an inclusion. So lo and behold, omega L of frob P is just the number P, has char poly x minus P independent of L. And this time, this is a miracle. This is a crazy miracle, because now as L, here this was bogus, right? The lambda just changes and changes. There's infinitely many lambdas, but it's all the same representation. Just the same representation being viewed as an L-adic representation by some silly construction. And this is different. The kernel of this representation is some number field that is some union of number fields that are more and more highly ramified at L. So this really does depend on L. You change L, you get a completely different kernel, and yet omega L of frob P is still P. Okay? And then the other example, third example, I won't do it, Tate module of an elliptic curve. Right? You've got some elliptic curve over Q, take its L-adic Tate modules, fpx is x squared minus ap plus p. There's just something, there's a compatible sequence, they're rational over Q. These things, they're completely different representations, but they all have the same traces in some strange way. So now I can start, because we've done all that. But so what did I actually want to say today? Start here, right. That's coming up later, compatible systems of L-adic Galois representations. The other thing I want to remind you of is that Grierson characters are not scary. So compatible systems of L-adic Galois representations are not scary. That's the first thing I proved today. And the second thing I'm going to prove is that Grierson characters are not scary, right? So here's the second theorem of the day. Remember Grierson characters. I'm just going to go with GCs, so I don't have to worry about strange German letters. Grierson characters. So here's the idea: K some number field. And then you have K star lives in AK star, which is some terrifying product that we talked about the other day, yesterday, to C star, continuous group homomorphism. So continuous group homomorphism is not scary. C star is not scary. This is a bit scary. So we have to talk a little bit about how unscary this is, right? So last time I explained in some detail, I did the case K equals Q, and I tried to convince you that this was not scary. And the reason it wasn't scary was because AK star turned out to be the product of Q star cross Z hat star cross the positive reals. And that's not scary because it's the positive reals. And this kind of has the potential to be scary because it's a terrifying, uncountably infinite pro-finite group. But what you've got to remember is that C star has no small subgroups, and this has a basis of neighborhood of open subgroups of the identity. So the bottom line is, when you look at some continuous map from this guy to this guy, it factors through a finite group. I'll just remind you, Z hat star, whatever this strange thing is, there's a surjection to Z mod NZ star, and I'll tell you what Z hat star is. It's just the limit of all these things. Right? Whatever that means, you take the limit of all these things, you get Z hat star. Whatever that is, I'll tell you something, limits come equipped with maps to the things that you were taking the limits of. So there's definitely a map from this to this, kind of by definition of limit. And all of these characters, every single Grierson character will factor through one of these maps because the topologies don't match up. This is some crazy, totally discontinuous thing, and this is, a sensible continuous object. So a Grierson character for Q, it's got to be on this, right? But it's got to be trivial on this. Here it factors through a finite group. So all we have to do is to decide what happens to the real part, and that's just a map x goes to x to the s, right? So, you can have z mod nz star, whatever, z mod nz star, chi to c star, and then you can have s, that goes from the positive reals to c star, just x goes to x to the s there. And that pair, chi and s, give you a character of this thing here, and hence a character of this thing here that's trivial on this thing here, and that's the definition, right? Chi comma s is a Grierson character. And if you could attach a number to that Grierson character, you could call it L of chi comma s, couldn't you? It's kind of what Tate did. So Tate attached the number by some integral. So not happy with that, I'm going to do another example. I'll do one more example, then we'll start. So final example, I'm going to do, maybe I'll do 2 more examples. We have to, if we don't understand Grierson characters, we have no chance. So we have to understand Grierson characters. So Grierson characters 2, let's do k is q of I, right? There's a random number field. It's not that difficult. There's finitely many units. That's the point. There's finitely many units. It's going to make life easy. Units are problematic, right? So Grierson character example 2, let's go. We've got to think of some map from AK star over K star to C star, right? What do Grierson characters look like for Q of I? I'll tell you something, a little knowledge is a dangerous thing. If you know about elliptic curves with complex multiplication, then there's an elliptic curve with complex multiplication such that the Tate module is somehow connected to some Grierson character. This is in Silverman 2. I remember being slightly terrified by this fact for a while, until I actually sat down and decided it was time for me to work out some examples of Grierson characters. So let's work out an example of a Grierson character. There was a little calculation involved in proving that the adels of Q broke up like this. So we've got to do some analogous calculation here. So let's try and I thought about it, and I have a better conceptual way of doing it, right? The adels of K are by definition the finite adels of K. So this is some strange kind of product of all the completions of K. K is a number field. And this is some strange product of all the completions of K, or loads of p-adic fields, times the infinite stuff. That's what the adels of K looks like. And in this case here, when you think about it, there's two maps, right, from K to the complex numbers. There's the obvious inclusion, sending I to the, to the thing above the imaginary axis. And there's its complex conjugate, sending I to the thing below the real line. So there's 2 embeddings from this into the complexes, but they're equivalent because one of them is the complex conjugate of the other. So this is one infinite plane. This is isomorphic to the complexes. But don't kid yourself, this isn't a complex manifold because that isomorphism is not, there's 2. And we can't tell the difference between them. So this is isomorphic to the complex numbers, but if you turned around and I replaced this by complex conjugate, you wouldn't be able to tell. That's how an infinite place works. It knows it's the complex numbers, but doesn't quite know how. It's just something that is worth, I don't know, sometimes it's just worth remembering. It's not really equal to the complex numbers. It's not even canonically isomorphic. It's non-canonically isomorphic. I'll tell you what that feels isomorphic. It's isomorphic to R bar. That's what it's isomorphic to. The algebraic closure of the real numbers, right? The algebraic closure of by general theory in Galois theory or something, the real numbers has an algebraic closure. So let's call it R bar. That's what K infinity looks like. Right, what should we do now? Oh, I'm going to give you a Grierson character. So what is this A? Remember what this means, the finite adels, AKF, it's just some totally strange, some restricted product over all P finite places, KP, right? And this means all but finitely many are integers. So let's do the units. The units of this finite adels are this restricted product of the unit, and this means this is some weird thing. This means all but finitely many for all but finitely many p. So this is an element in the actual product is xp, right? For p a prime ideal of k. So for all primes p, we got some random number, but that's not allowed. This thing is too big. This is much smaller, right? Without the funny little prime, it's much too big. That funny little prime means that the p-adic valuation of xp is equal to 0 for all p not in a finite set. And the weird thing about this construction is the finite set's allowed to move. All we ask is that it's finite. Okay? And it occurred to me last night, thinking about what to say today, was that there's a really obvious, I'm sort of saying, it's a bit scary, there's a finite set, we don't really know what it is. But actually, we can use this to our advantage, because there's a really, really simple construction. Note the following rather simple construction. Note the following simple construction, which was implicit in what I said yesterday. Given an element of this terrifying finite Adele thing, so what we have for every single prime ideal of OK, we have an xp, and the p-adic valuation of xp is 0. So look, what I want to do, let's define np. So given this x, which is this crazy amount of information in this finite Adels, given a finite idel x, let's define an integer np in Z for each prime p by np is just the valuation, the p-adic valuation of xp, right? So these are completely unrelated p-adic numbers as p varies. That's what this strange object is. A whole bunch of completely unrelated p-adic numbers. And all we know is that all but finitely many of them are units, right? So what do we know about these MPs? They're completely unrelated integers. Okay, so this is p running through the finite places of k. So the MP, completely unrelated integers. And all I have to do is satisfy one criterion, which is for this to be an idel, this has to be a unit for all but finitely many p. So the NP are completely unrelated integers satisfying one condition such that NP is equal to 0 for all but finitely many p, right? So given a finite idel, there is a construction of infinitely many completely random integers, all but finitely many of which are 0. So I've got an integer for each prime ideal of k, and then it occurred, this is something that I really should somehow explicitly spell out. I've got an integer for each prime ideal of k, and all but finitely many of those integers are 0, so I can just build an ideal, right? Let me define an ideal. Well, I suppose, strictly speaking, it's a fractional ideal. Right? It's just kind of I of x, right? So this is some ideal living in k. All the integers release it. It's just I of x is just simply the product over all primes p of p to the power np. That's a finite product. That's what the idels give us, right? It's just a finite product. It's just an ideal of the integers of k. If the MPs are less than 0, I suppose that, strictly speaking, could happen, then it's a fractional ideal. But if you don't know anything about fractional ideals, just pretend all the MPs are positive, right? All the non-zero MPs, just pretend they're positive. Then this is just an ideal, right? So what I'm saying is, given a random idel, a finite idel, there's a really easy way of just constructing an ideal. Right, so lo and behold, I get, so Ix, right? E.g., if all the MPs are greater than or equal to 0, then I of x is just a non-zero ideal in the integers of k. It's as simple as that. And so this construction gives you a map from the finite idels just to the non-zero fractional ideals. So there we go. AKF star goes to non-zero fractional ideals. Fractional ideals of K. If you don't know anything about fractional ideals, the ideals, of course, ideals don't really form a group. You can multiply two ideals together, but like if I've got the prime ideal n living in Z, then I can't I can't do an ideal times another ideal is equal to all of Z. I mean, what would the other ideal? The other ideal would have to be 1 over n times Z, right? That would kind of be good. That's a perfectly good set, right? This is A over n for n in Z. Right? But it's not an ideal. If that was an ideal, that would be brilliant, because like 1 over n times n would be 1, and ideals would form a group. But it's not an ideal because it's not even in Z. Well, it's a fractional ideal. So what a fractional ideal is, it's just like an ideal divided by a number. So if you do fractional ideals, then they have factorizations, and they look like that, but the factors can be negative. It's kind of a useful tool when you're defining class groups. So there you go, AKF star goes to fractional ideals, and it turns out if you think about it, K star kind of goes to the principal ones. And so this quotient here that we've been going on and on about somehow maps to the class group, which is kind of, I don't know. Let's get back to the point. We're doing Q of I, right? We're doing. I'm teaching you that Grierson characters aren't scary. So let's do a scary field like Q of I, because that's not Q, so it's inherently scary. And let's figure out. So let's back to Q of I. So we've got to define. We've got to write down some Grierson characters. So they're going to be characters of AK star, right? Well, that is by definition the finite L's, about which we've just said something, multiplied by the infinite ones, K infinity star, which is non-canonically isomorphic to C star. Okay? So we've got to write down a character of this thing here. And I'll tell you what I'm going to do. And of course, remember, this contains K star. This is embedded diagonally. And my claim is, if I have some random, I'm just going to claim this. AK star is K star dot the product for all primes P, OKP star times K infinity star. There. This is a very fancy way of saying that K has trivial class group, right? In other words, K has class number 1. These statements are the same, right? So let's see it. So here's why. Here's the proof. If I've got X in AK star, why don't I write it as X is the finite part times the infinite part, right? So the infinite part, that's a complex number, and the finite part is in the finite ideals of K. And I just explained a construction. So that's a random bunch of p-adic numbers which are completely unrelated, all but finitely many are integers. I can take the p-adic valuation of xp, and I'll get some number. I get a number for each prime ideal of K, and I take all those numbers and I put them together to make that gadget there. So xf becomes I of xf, and that's a fractional ideal. That's a fractional ideal of K, and so it's principal. So it's generated by lambda. This is what I'm doing. I proved this for K is Q yesterday. And I kind of proved it by example. I wrote down a random ideal, and then I goofed around with it until I put it in there. And now I'm doing the same proof, but in a slightly more sophisticated manner. So if you sort of understood the previous proof, then this proof will somehow make a little bit more sense. So I of xf is a fractional ideal, so it's a principal fractional ideal, so it's generated by lambda, right? And when you think about it, if I look at xf divided by lambda has p-adic valuation 0, right? So this is xp divided by lambda, right? For all primes p of K. That's what a Finaliter Daily is. It's just a bunch of collections of p-adic numbers. And this has valuation 0, right? The p-adic valuation of xp over lambda is 0, right? Because that's the definition of lambda, right? Vp of lambda equals Vp of xp by definition. That was how we defined lambda. Vp of xp, that's the power to which p occurs in this I of x, and this I of x is just principal, and so it's principal, so the factor of that ideal lambda, and you get product p to the mp, where mp is the valuation of lambda. So these are the same, and so the valuation of that is 0, right? And so do you see we're finished? So whatever this xp over lambda is, it's in the idels, but the valuation at every single finite place is 0, so it's in here, you see. Therefore, xf over lambda, xf divided by lambda is in the product over all p's of okp star. So I've proved this claim. And then at infinity, I'm not making any assertion. At infinity, I'm just saying there's something happening at infinity. You see, so this is there's nothing to check at infinity, because I'm just allowing. What I've done is I've taken a random idel, I've magicked up an element of k, I've divided by that element. This proof works for any number field of class number 1. I don't think I even ever assumed it was Q of I, did I? That's done class number 1. So now, but the point is, so this is proof. This works for all k with class number 1. There, that's a proof of that. So in particular, it works for Q of I, because Z of I is a principal ideal domain. What I'm actually trying to do, though, is I'm trying to give you a feeling for what a Grierson character is. Okay? That's the goal here. I mean, I guess a secondary goal is to give you some feeling for what the idels are, because I think these are a vastly complicated object, especially if it's the first time you've seen them. So a consequence of all this, so a consequence of claim, if k is a number field with class number 1, we'll come back to Q of I in a second. If k is a number field with class number 1, for example, e.g. Q of I, all I need is that every ideal is principal. I need that every ideal is principal to, that's the where I used it, right? Class number 1. If k is a number field with class number 1, e.g. Q of I, then to give some Grierson character, to give that, well, this group is generated by these, where's it gone? Here. This group is generated by these subgroups. So to give some character that's defined on the entire group, all I have to do is say what's happening on these subgroups. And when you think about it, we're sort of in good shape here, because this subgroup here, the thing has to be trivial, because that's part of the definition of a Grierson character. And this subgroup here is not scary, because continuous group homomorphisms from this, admittedly this is a bit scary, but the point is all these sides are going to factor through finite quotients here, so there's just some finite piece of combinatorics, and then we have something that looks like the complex numbers. Okay, so at the end of the day, to give psi from k star to ak star to c star, right, is to give psi on this, which is trivial. So all I have to do is to give psi on this, right? Is to give psi restricted to this thing here, product of okp star cross k infinity star. Right? All I have to do is to give psi on this, except there's a catch, right? Product of okp star cross k infinity star to c star. Except that this isn't a direct product, right? There's things that are in this and in this. So this isn't, if this was beautifully some product of this group and this group, then when I try to give a character of this group that's trivial on this group, all I have to do is give a character on this group. But here there's a little bit of overlap. So there's a little twist There's a twist in the tail here for Q of I. So it's to give psi one of these things here, a continuous character, such that psi is trivial on the intersection. And this is a little bit muddly to think about. This is diagonally embedded K star in AK star, intersect product over all primes P of OK P star intersect K infinity times K infinity star. So we're going to have to work out what this is, because this is a condition. To give a Grierson character, all we have to do is to give some finite amount of data and a map from C star to C star, which probably we're going to be able to cook up. But there's a catch. So let's figure out what the catch is. So an element in here is some lambda, and then of course that goes to lambda, 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 right? So this element of K star, if it's in all of these things here, then this says for each prime P, P doesn't divide lambda, right? So this is lambda, which are not a multiple of 2, not a multiple of 3, not a multiple of 5. They're not a multiple of anything. That's what it means to lambda here. So this just means, so this means that the p-adic valuation of lambda is 0 for all primes P. And obviously at infinity it says nothing. It just says it exists. So this is no condition at all. At all the finite places, this is a condition. It says I'm prime to P, right? So that just says lambda is a unit, right? Lambda is in OK star. These are, what I'm saying is a global object, which is a local unit, is a global unit, right? Unit means, unit means if it's a function and it doesn't vanish anywhere, it's an invertible function. Has a reciprocal, you see? That's all I'm saying. So lambda is a unit, lambda is an OK star. OK, so if K is Q of I, then OK is Z of I, and the units in that, OK star, is plus or minus 1 and plus or minus I. So to give a Grierson character for Q of I, all I have to do is take some finite character here. Let's do it now. There's no point me. There's no point me saying the same thing again and again and again. So now let's just write down an example. Let me show you how kind of trivial it is to write down a Grierson character for Q of I. Right, so here we go. So here's an example of a Grierson character for Q of I, GC for Q of I. Okay, well let's take Z of I. Let's just choose a random level, right? This contains n, which is my level, which is just some non-zero ideal. Okay, and then let's do Z of I modulo n. That's a ring, that's an ideal. This could just be the principal ideal generated by 24, right? This could be anything. There's a random ideal. It is principal. They're all principal, right? I quotient out this ring by this ideal. That's a finite ring. I take its units. That's a finite abelian group, right? So let's just take kind of a Dirichlet character. So I mean, it's not quite a Dirichlet character. There we go, right? So here's an example, right? So I take a random. This is a random one-dimensional representation of a finite abelian group. Okay, so that's nice and easy. I mean, here's an example. N could be the prime 2 plus I. That's one of the prime factors of 5. Z of I modulo 2 plus I. You take the quotient, it's just Z mod 5. This is Z mod 5. This is Z mod 5 star. This is a cyclic group of order 4. This is some random representation of the cyclic group of order 4. So the generator to I. So there we go. There's the chi part. Let's do the infinity part. So you see, this is chi gives us. What's the point of this chi? This chi gives us this crazy product over all p's of OK P star, right? I want to call that OK hat star. That's quite good notation for it, because it is some kind of algebraic completion of OK. I should maybe take the integers of your number field. That's like z to some power. Then take some profinite completion, z hat to some power, and then take the units in that. This is some gadget that's a little bit scary, but you've got to remember that it just surjects onto this guy here, right? OK modulo n star, right? K is Q of I, so this is, and so now I've got chi, right? So great. That's a really non-scary thing, and that's done this bit. Product over P of OK P star. That's done what, to be quite frank, is the scariest part of the Adels, right? The kind of crazy pro-finite. So now what we've got to do is decide what's going on in the infinite part. In the infinite part, I need to give a map from C star to C star, right? K infinity is isomorphic to C star, and I need to think of some map to C star, something that's going on at infinity. And then I've got to remember this isn't not really canonical, so I don't really want to start thinking of holomorphic functions from C star to C star. I'm just going to do the stupidest thing, right? This is the set R e to the I theta, right? Complex numbers. Theta is some angle and R is a positive. You know what that notation means, right? Is R e to the I theta. So what is R? R is in the positive reals, right? And what's theta? Theta is an angle, and I can think of all angles as just being S1, right? So that's what the non-zero complex numbers looks like. So I've got to think of a map from the positive reals cross S1. So S1 to C star, S1 is, of course, I can just think of it as Z, such that the norm of Z is 1, right? So I've got to think of a map from S1 to C star. I'll just send Z to the power n, right, for n some random integer. Okay, so I'm trying to think of a pretty general class of maps, group homomorphisms from C star to C star, break up C as a group, it's a circle, the unit circle, and what's left is the positive real, the norm of your complex number. So abstractly as a group, there's the positive reals cross a circle, character of a circle is nice and easy, I'll just send Z to Z to the n. That's all of them, right, in some sense. I mean, in every sense. That's the only representations from S1 to C, the only continuous ones, they all look like that. The Z goes to Z, we don't need that fact, it's just like, it is true. And then similarly, the real part, R bigger than 0, that contains X, and that can go to X to the power S, right, in C star, where S is just a complex number. Okay? So what's going on at infinity? So the upshot is, if we just choose some random s in the complex numbers, and we choose some random n, an integer, then I give you a map from k infinity to C star. Then I get a map from k infinity star, isomorphic to C star. This is isomorphic to R star cross S1, right? Well, let me just I don't even need to, C star contains R e to the I theta. There's your general complex number, and that's going to go to R to the power S times e to the I n theta, right? Looks a bit weird, but it looks a bit weird because it's not holomorphic, you see. For example, how would you do complex conjugation? The complex conjugate of R e to the I theta is R e to the minus I theta, right? So complex conjugation would be S is 1 and n is negative 1. Right? And like if you just have S is 1 and n is 2, it's not any kind of map you've seen before. It's just I guess you could do Z goes to Z to the n. That would send R e to the I theta to R to the n e to the I n theta. So if S equals n, then that's just a Z goes to Z to the n. But if S equals 1 and n equals negative 1, it's complex conjugation. What am I trying to do? I'm trying to explain to you that Grierson characters for Q of I are not difficult. So I'm trying to write down a map from this terrifying looking thing to C star, and the thing that was down here, some lemma said that if K had class number 1, then all I had to do was to say what was going on this big pro-finite thing here and what's going on at infinity. And the big pro-finite thing I've just shown you, we can just write down loads of maps. And at infinity, we can just write down loads of maps. But now there's a problem, because they have to glue. I mean, what's the glue? Right? So we take all this data. So upshot so far is that given a random chi, given chi from Z of I modulo n star to C star, finite group, easy thing, n, an integer, easy thing, s, a complex number, an easy thing, Given those three things, we can get some size 0 from the product over all p of OK p star cross k infinity star to c star. Okay? So given some easy data, we can get a Grierson character. And now the question is, well, it's not a Grierson character. That's the problem. I've defined it on this subspace. There's a catch, right? And we can see it here. Consequence of claim, if k is a number field with class number 1, like Q of I, to give an actual Grierson character, that's what we're interested in, is to give this restriction to this stuff here, a continuous character. There's going to be a such that somewhere. It's gone. There's an issue with units. Yeah, it's gone. We get size 0 from this right, so the problem is, we get size 0, and then the problem is that maybe size 0 maybe does not extend to a Grierson character because of this stupid fact that it's this cross k star, because maybe size 0 is not trivial on OK star, right? Which is plus or minus 1 and plus or minus I. So it was looking so good, we could just take a random collection of objects which are easy to understand, we put them together, and we might not get a Grierson character because now we have to do some technical calculation to see what's going on in these global units and to see if it works. So here's a fix. We've got this size 0. Consider size 0. Size 0 is a group homomorphism. So let's just consider size 0 to the power 4. Okay? That's going to kill it, right? These elements have all got order 4, right? This has OK star is now in the kernel. So you raise chi to the power 4, and you multiply n and s by 4, and all the problems have gone away, right? And so that extends to a Grierson character. That goes over here. So there we go. Consider size 0 to the 4. Size 0 to the power 4 will extend to psi, right? To psi from k star over ak star to c star. Okay, so now we've kind of even got a feeling. Or like, if you don't like taking it through, you could imagine instead we've got a 1 in 4 chance, right? You could think about it that way. Given a random chi and an n and an s, you've got a 1 in 4 chance that this is going to die on. You can see what the issue is. The I is some random thing, so I lives in this, right? I is a unit in zi, so I is certainly an invertible element of this group. So chi of I guess chi of I is just some, we don't know what it is. Chi is random, so chi of I is some random thing, and then we could work out what happened to if let's just do this. R would be, I'm trying to work out what I is. R would be 1, and theta would be 90 degrees. There's this thing called radians. I never really got the hang of it. So you're going to have to bear with me. This is 90 degrees, 180. Yeah, it's just R. It's R is 1. S is irrelevant. R is 1. S is irrelevant. Right. So I think that this random choice here sends I goes, I'm trying to work out size 0 of I. And it seems to me that it's chi of I multiplied by I to the power n. So this would be another way of doing it. You choose chi randomly, and then you see where I goes, and then you choose n appropriately in some certain congruence class mod 4 to make sure that this is trivial. And the moment this is trivial, you're then trivial on this intersection, right? Remember, this is the issue, k star intersect product OK star cross k infinity star. If you make sure that size 0 is trivial on this, then it will extend, right? Because everything in here is a product of something in here and something in here, because it's got class number 1. So it's a finite amount of data modulo some finite congruence issue, and that's it. Right? And in particular, if you look at the set of all Grierson characters, we can kind of see what it is. There's some discrete stuff, there's some more discrete stuff, and there's one smoothly varying complex parameter, and that's your parameter on your Tate your Tate complex analytic eigencurve attached to GL1 over K. It's a Riemann surface. There's your complex structure. So there's that. I'm going to do one more example. I'm going to do Q root 2. Because Q root 2, there's one more phenomenon. Q root 2 has infinitely many units. So if I do Q root 2, where there's units, then you've seen every phenomenon. And so then you can work out a Grierson character for any group at all. Right. So worked example 3, and then we'll start the lecture. So worked example 3. Is that K can be Q root 2. And Q root 2 in this context is a terrifying field, because Q root 2, the integers of K are Z root 2, right? And Z root 2, the units come up, right? Z root 2 star is infinite, right? This is an abstract group generated by plus or minus 1 cross 1 plus root 2. Right? This is clearly a number which is not a root of unity because it's 2 and a bit. So you raise it to the power of 1,000,000, you'll get a really big number. So this is not a root of unity. This is the group generated by this is what I mean. Not really. Plus or minus 1 cross the group generated by 1 plus root 2. 1 plus root 2 times 1 minus root 2 is negative 1. So this is a unit in this ring. This ring's got infinitely many units. So do you see, this is a new twist, because at some point we had some guy and we had to make sure it was trivial on the units. So it was like, the units are finite. It's got order 4. Let's just raise it to the power 4. So let's just do this, just so we get the hang of what happens in this real quadratic case. So this will be quick because all the machinery is there, right? K's got class number 1. Every ideal is principal. K class number 1. Okay, and therefore AK star is going to be K star dot the group generated by product over P OKP star cross K infinity star, right? And so we've got to give a representation of this that's trivial on this. We just have to give a representation of this, but then we have to make sure it's trivial on the intersection. Okay, representation of this, nice and easy, right? Representation, well, a character of product over P OKP star. All you do is you take Z root 2 modulo Z root 2 modulo some ideal, take the units, take some random map, chi to C star, that's it, right? This surjects onto this, that's a fact, that's how it works. Every single continuous character of this factors through a finite quotient, that's all it is. So we've got a character of that bit. K infinity star, well, we're going to have to think. K infinity star is a different story now, because Q root 2, there's 2 maps from Q root 2 to the reals. One sends root 2 to plus root 2, one to minus root 2, and they're not in the same equivalence class because they're both real. They're not complex conjugate anymore. They're conjugate in some other way, and at infinity we can't see that other way. At infinity they're just 2 different things. Right, 1 plus root 2 to the power of 1,000,000. One of these maps sends 1 plus root 2 to the power of 1,000,000 to a gigantic number. The other one sends it to a really tiny number, because it sends it to 1 minus root 2 to the power of 1,000,000, and 1 minus root 2's got norm less than 1. So these are 2 utterly unrelated, completely topologically different copies of the real numbers. So this is R star cross R star. So I'm trying to give a character of this thing here, and I'm going to give a character of this, which is just a finite piece of data about which I'll say no more. And I'm going to give a character of this guy, and this guy is 2 real numbers. Normally we only have 1. We had 1 real number, we had 1 complex number, which was a real number then a circle, but now we've genuinely got 2 real numbers. So here we have more space. Great. So we want to do kind of chi infinity from K infinity star to C star. We've got to choose, right? Chi infinity, we can call it x1 of x2. Those are 2 real numbers. This can be x1 to the power of s1 times x2 to the power of s2. Okay? So we've got 2 degrees of freedom. So what have I given you? I've given you chi, character of this finite part, chi infinity, character of this infinite part, and so I've given you a character of that big thing in the brackets here, right? So there we go. So we get psi 0 from product of O, K, P star, cross K infinity star to C star. It's just the product of those two things. So size 0 of whatever, the finite part and the infinite part is simply going to be chi of the finite part times that thing there, size 0 of the infinite part. Okay? So it's a finite amount of data, Dirichlet, an analog of a Dirichlet L function. That's all it is. And then two complex numbers, S1 and S2. Okay, so size 0, when does it extends? It extends to a Grierson character if and only if size 0 restricted to the units embedded diagonally is trivial. So we've got to figure out what this says. So for the imaginary quadratic case, this said size 0 restricted to a group of order 4 was trivial. And I just said we could just raise it to the power 4. That would make it trivial. Multiply all our parameters by 4. But here, this is an infinite thing. So maybe in theory, there's like an infinite number of equations we need to satisfy. Well, actually, it's not as bad as that, because even though it's an infinite thing, this group is finitely generated. So we ought to make sure that some group homomorphism kills a group. We just better make sure that it kills all the generators. So this thing here is a finite number of equations. And I'm just going to work out what those equations are in this case. Because for a general, here's what's really going on. K is a general number field, okay? This isn't true. This isn't true because for a general number field, the class number is finite. So this contains this as a finite index subgroup. So first you do some combinatorics like this. You get a finite Dirichlet character, finite number of complex numbers, maybe some integers if we've got C stars. We get that kind of data, and then we have to solve this equation, make sure it's trivial on the units, which is going to be some relation amongst the data. And then we've got a character of this guy here, and then we just say, and then we just have to extend it by a finite amount, like make it a finite amount of extra choices. So for a general Grierson character, that's the formula for what a Grierson character looks like. Okay, finite combinatorial data, and then something. But then this finite number of equations, what do they really look like? If we could figure out what those equations really look like for a general number field, we would completely understand Grierson characters. And I'm not going to do it. I'm going to do it for Q root 2, because if you understand it for Q root 2, you understand it for everything. It's kind of how it works. Right? So I'm going to press on and do this calculation quite carefully. And once we've done that calculation carefully, we will have understood what a Grierson character for AK star looks like if K is Q root 2. And hence, we will have understood it for every number field, because I will have shown you all the phenomena. Right. Whatever does this all mean? Size 0 of OK star. Well, size 0, OK star. So K is Q root 2. OK star is rather irritatingly plus or minus 1 across the infinite group generated by 1 plus root 2. Okay, this is fine. This is a group of order 2, right? Group of order 2. We have to make sure we're desperately trying to define a Grierson character on AK star. So far we've got this size 0 that we've built in some explicit way. So this group of order 2, let's just think a little bit carefully. What have we've got like? I don't know. So I mean, I'm telling you lies, aren't I? This is not quite. There's more noise here. R star. I'm not sure I can do this if x is negative. I think I'm going to have to do this there times some plus or minus 1 thing, right? I've lied to you. The characters of R star cross R star, I think x goes to the naught. There's a plot. I'd forgotten about this. We had R bigger than 0. The characters of R bigger than 0 are x goes to x to the s. I've just noticed this is a little bit bigger than positive reals. This is all the reals. So there's some. I'll take norm of x1 to the s1, norm of x2 to the s2 times the sine of x1 to whatever, to 0 or 1, times the sine of x2 to 0 or 1. There's some kind of annoying sine thing. And lo and behold, this is some annoying sine thing, right? This will fix this up with choices of sines. Okay, so there's just some stupid sign noise, but this is the issue. This is the issue, because this looks like the much more complicated thing. I can guess what the answer is, though, because I told you that Tate's complex analytic eigencurve was the base space for where L functions are defined, right? And if you know about the Dedekind zeta function of a number field, you know the Dedekind zeta function of a number field is a function of one complex variable. And maybe you've seen papers with titles such as like multivariable p-adic L functions in Iwasawa theory or something. So you're well aware that maybe p-adic L functions can have 2 or 3 variables. These classical L functions that most people consider, you know, these things discovered by Hecker tended to have one complex variable. So there must be something wrong here. We've got two complex variables here, and that's too many. Because if this turned out to be no condition at all, this 1 plus root 2 business, our Tate's complex analytic eigencurve for k would be 2-dimensional, and the L function, the zeta function of k, the Dedekind zeta function of k, would have 2 parameters. So what I'm suggesting is, at the minute, we've got too many degrees of freedom, right? This is just some stupid noise about the signs, and this is just some stupid noise, some finite order Dirichlet character. But this says, I have 2 complex degrees of freedom, and that can't be the right answer. So trying to figure out what happens here with 1 plus root 2, you see the answer. So let's look at psi 0. Psi 0 of this psi 0 of 1 plus root 2 is supposed to be trivial. Okay? So we better think about what this means. So this is 1 plus root 2 embedded diagonally. By 1 plus root 2, I mean, that's an element of k, so it's an element of kp star for all primes p, so it's an element of okp star. And then it's also it's a random real number, right? Well, there's 2, right? You've got to be careful. There's k infinity is 2 maps from k to the real numbers, and we've got both of them, right? So this 1 plus root 2, it kind of becomes 1 plus root 2 for one of them, and 1 minus root 2 for the other one. Okay? So it seems to me that what this says, so at the finite places, there's just some finite amount of noise, right? At the finite places, there's some kind of generalized Dirichlet character, and this will just go to some root of unity, right? And then at the infinite places, I guess also there's a certain amount of noise, because 1 minus root 2 is negative, so the sign of 1 minus root 2 is minus 1, so there's just some choice here of a plus or minus 1, and that's a little bit of noise as well. So this seems to me, the noise is just some roots of unity. This seems to me to say, though, that when we look at this bit here, this is the terrifying bit, the moving bit, the S1 and S2, this seems to me to say that 1 plus root 2, the norm of this to the power of S1, times 1 minus root 2, the norm of this to the power of S2, must be some root of unity. Right? That's what it says. So there's our condition. If we can make that condition, and not only that, has to be the right root of unity, right, that comes out from all the chi and the signs and blah, blah, blah. So that's what our condition says. And if we can solve that condition, then we've kind of nailed Grierson characters for Q root 2. So how are we going to make that? We have to make, that's kind of a weird thing, right? 1 plus root 2 to the S1. So if 1 plus root 2, if 1 plus root 2 is x, then 1 minus root 2 times x is minus 1, right? Because it's 1 plus root 2. And therefore, the norm of 1 minus root 2 times x is 1. Therefore, 1 over, right, so 1 minus root 2 is actually 1 over x. Okay? So what this says, so what we need is that x to the power s1 multiplied by 1 over x to the power s2 has got to be 1, right? There's our condition, where x is a pretty random, let's face it, real number. It's 1 plus root 2. So that's what we need, or, you know, we need some root of unity or whatever. So that's what we have to solve. And how are we going to solve that? So that's like x to the power of s1 minus s2 is 1. That's the equation we need to solve. And now all of a sudden you can see that we don't have 2 degrees of freedom anymore. Right? It looked locally like we had 2 complex variables we could choose, because the infinite places we had 2 degrees of freedom. But no, the units give us a relation. And that relation says that a random real number to some power has to be 1. And so the easiest way to solve this is just let S1 be S2, right? That will work. If we let S1 be S2, then everything will work. And if we don't let S1 be S2, then we're very limited in our possibilities, really, because this has definitely got to at least be a root of unity. I think letting S1 be S2 is probably the safest idea. What's the answer? I don't quite understand this. S1, I'm just 1 plus, can't I have 1 plus the square root of 2 to the power of s? That's allowed to be whatever, some cube root of unity, isn't it? Zeta 3. What does s look like then? See, if s was 0, then it would be a first root of unity. I just need to, hang on. Just talk amongst yourselves. X of s log 1 plus root 2. Oh, no, wait. No, but log of this. Oh, crap. Log of, I don't want to do that. Oh, no, I see. S log 1 plus root 2. I see. It's e to the s log 1 plus root 2. It doesn't have to be 1. It is allowed to be a root of it. So this would be e to the 2 pi I over 3. That would be OK. And so s doesn't have to be 0, does it? S doesn't have to be, that's a very obvious choice. S1 equals S2. But in fact, you can have, it's a discrete invariant. This thing here, the correct answer really is that this has to be a root of unity, right? Because remember, 1 plus root 2 is just some random element of this, and we've got some random Dirichlet character chi. So this just goes to some random root of unity. So we don't have to have S1 equals S2. We are allowed, S is allowed to be, it seems to me that S is allowed to be a rational number times pi times I divided by log of 1 plus root 2. Right? That's strictly speaking the answer. And what I want to suggest is that that's actually discrete, right? So that's still, yeah, this is S1, take away S2, must be in some discrete set. And so we don't really have 2 degrees of freedom. What we actually have is one complex variable and then another amount of discrete data. Right. Let's not worry about that discrete data, because I didn't really know it was there until about 2 minutes ago. Let's so let's stick with S1 equals S2. So here's the upshot. If I have chi from z root 2 modulo some ideal n star to c star there, and then I've got psi infinity from r star to r star. No. R star cross r star to c star. So this is just a random group homomorphism. So this is psi infinity of x1, x2 is norm x1 to the power s, norm x2 to the same power s, times the signature of x1, the sign of x, this is a plus or minus 1, to some 0 or 1 times the sign of s2 to the power 0 or 1. Then up to finite order, then the corresponding psi 0 from the product over p, OK p star, cross k infinity star to c star, up to finite order, because there's some root of unity issue. to some finite power which makes all the roots of unity match up, extends to some psi from k star over ak star to c star. So when you actually explicitly want to work out Gerson characters, these are the calculations you end up doing. And at certain times in my life, I've just sat down and had to do such calculations. And I've just done some in front of you right now. So that's how it works. You get discrete amount of data and then one place of complex freedom, right? So Tate's C-analytic eigencurve is one-dimensional again. And even for a general number field, when you do the, I mentioned this yesterday. Even for a general number field, you look like you've got lots of degrees of freedom at infinity, but then you've got lots of units that are cutting you down, and you end up with 1 degree of freedom. Right, so now I'll start the lecture. That was an illustrative example of what we're going to be talking about today. Oh, wait, it's time to stop. OK, right, I'll start the lecture at 11.